Now we should learn that how we can apply the loadings and how we can apply the earthquake load, wind load on this particular structure and arrangement. What are the different kinds of loading also that can act? So we can go to the load patterns here, and in here we do have a case of SIDL, and instead of that SIDL we can name it as piping load. So whatever piping load that is being provided to us by the piping engineers, that we can enter into the piping loading arrangement. And we do have live load also, because ultimately we may have to consider a case where a person or 2 to 3 engineers may go up and do the maintenance of the piping if there are as such requirements. And dead load, obviously it has to be there with sulfate multiplier. Now the sulfate multiplier has to be as per my experience in the range of 1.15. Now why we are providing sulfate multiplier as 1.15 is that there are a lot of structural steel connections that go into the, we can say, execution. So there may be the heavy bolting here. There shall be plates also installed, and there shall be angles, gussets, cleats that needs to be installed for the structural steel connection design. And as per my experience, if we are proceeding with the bolted connection, so in that particular case, the additional weight, it is usually in the range of 15% to 18% of whatever structural steel tonnage that you are calculating. So let us say this particular pipe rack weight is approximately 10 metric ton, or we can say 10,000 kg. In that case, the total fabrication, it should not be only 10,000 kg, it shall be 10,000 kg plus 15%, considering the weight of the bolts, plates, gussets. So total weight shall be 10,000 into 1.15, that is approximately 11,500 kg. So that is the number that we do need to take into account while designing the foundations, while considering the earthquake forces, and obviously while estimation of the structural steel that is being used. So that is done, and after that we can go to the plan view here again. Click on level 1, and here we, instead of one story, we can again select all stories so that we can save our time. So in here, let us say, yeah, for clarity, we can just simply switch on the end releases also. Click on apply and okay. So let us say that in our case, we can assume that as per the piping engineer requirement, on each and every beam, we do have a, we can say, let us say 303 kilonewton per running meter of the loading that is acting on each particular steel beam. We do need to understand that this is the loading that is provided by the, we can say, uh, piping engineer itself. So we can go to the assign frame loads and distributed. In here we can select the loading as 3 kilonewton per meter. Direction has to be, we can say, gravity only. So we can apply that under the piping section and apply. So now it is okay. And after that, let us assume that we can go to the display and undeformed shape, and we can click on the 3D window also. Yeah, so now we can see that on all the floors and on all the beams, we have applied 3 kilonewton per meter of the loading. After that, as a second input, they do provide the lateral forces also. So let us assume on each and every, we can say, floor at this particular point, or on this particular steel beam, on this beam and on this beam, let us say we do have a lateral force also that is also acting. So not on this, but on this. So let us assume we do have a, we can go to the assign frame loads and point load. So let us assume that we do have 10 kilonewton of the point load acting along the x direction, that is global x. So not on this point. Here we can enter 0.5, that is acting at the midpoint, and here we can apply 10 kilonewton of the point load. So here we can see that now 10 kN of the point load is acting along x direction. And under the same case, let us assume that we do have a we can say 5 kN of the point load acting along the y direction also. So we can select all of these beams again, click on apply. So now we can see that we have applied the lateral forces also. One thing that is done wrong here, we do need to select the piping load. We do not need to select the dead load here, because these lateral forces and all that is a part of the piping load itself. We can just click on delete existing load, and instead of the dead we can select the piping here again, replace, or we can say add to existing load. We can add the global y direction here, and in here we can select the 5 kilonewton load. So now we can see that the loading has been applied, and similarly we can apply the loading on the remaining beams also. So now 5 kN of the point load has been applied along the y direction also. We can check that in the 3D view here also. So now we can see that how the loading has been applied on the y direction along all the beams. So that is now concluded. That is, we can have applied the self weight of the piping also. Here we can click on loads. So we can see that uniform force is 3 kN per meter is applied along the vertical direction. Self weight of the pipe, self weight of the liquid or the gas or the steam that those pipes are handling, that we have already assumed here. And we have applied, or we have assumed that at the locations that where we have provided bracing, there are large amount of thermal stresses or thermal loads also that are coming, that have been made as part of the piping load itself. So if we click on this particular steel beam, the one that we have locked with the help of the bracing arrangement, so here we can see that the point force of 5 kN per 5 kN has been applied in the, we can say, y direction here, and 3 kN per meter has been applied along the vertical direction. So what we need to do here is that we do need to add the horizontal force also here. So I think that has been replaced here. So assign frame loads and point, and as already y loading has been applied, so we can click on add to existing load, and along the, we can say, global x. In here we can select the distance ratio as 0.5, and in here we can apply 10 kN of the point load. So if we check the loading here again, so two types of point loads have been applied, that is 5 kN along y and 10 kN along x. So that is also okay. Similarly, we can repeat the exercise on all of the other beams also. So here also and here also. So we can, click on apply. So now we have applied the 10 kN of the point load on these beams also. In here, we do need to delete the loads, because we do have only lateral, or sorry, vertical load or gravity load on all these steel beams. But in here, we do have two kinds of point load. Yeah, so if we are selecting this particular beam, now it is okay. We can left click on escape. So on this particular steel beam, we just need to delete the existing loads and apply the load again, because loading had been applied 2 times. So we can just delete all of these beams here and replace existing load. For x, we can apply 10 and then click on again add to existing load 5 and global y. Select these beams here again, click on apply. Just left click here and then right click. Now it is okay. So 10 kn along x and 5 kn point load along y. Similarly, we can check here also 10 kn along x and 5 kn along y. So yeah, so now we can just close this window, and we can assume that we have already applied the dead load with the connection margins also. Piping load also, that also we have assumed and applied, but the overall philosophy is now clear to you that we have to consider the weight of the piping also, and we have to consider the weight, sorry, the lateral forces also that might be acting as per the piping engineer inputs. For the supporting arrangement, now we can assume that all of the supports have been considered as fixed here. Because if we're going with the pinned pipe rack for this particular height, the arrangement shall be much heavier. So we can go to the assign joint restraint, left click on fixed and apply. We can go to display and undeformed shape. We can again go to the default 3D view here also. So now we have applied the fixed support also at the bottom. Next step shall be that we can check the earthquake forces also. So we can go to the load patterns again. As you know, this is a standard theoretical problem. We can assume the loading. So we can click on modify lateral load. Eccentricity ratio, that has to be 0.1. There is no doubt in that. The story range, it has to be from the bottom to top. That is from base to level 3. Site subsoil class, we can assume it as B. Probability factor KP, hazard factor Z, performance factor SP, and ductility factor that is U. That we can refer from the code itself. Under this particular case, we can assume that the frame that we are designing is basically concentrically braced frame. We have not considered any eccentric braced frame here. In earthquake, in the language of earthquake, we can say that performance of eccentrically braced frame is much better as compared to the concentrically braced frame. So that is why here you can see that U factor is higher as compared to the limited ductility. That is this particular one, that is 2. So we can assume that the frame that we are right now dealing with, that is not an ordinary moment resisting frame because we have provided a lot of bracing. So this option is closed. Moderately ductile concentrically braced frame and limited ductile concentrically braced frame. So we can, as you know, we are not making this in the New Zealand, but we are making this in Australia. So we can proceed with limited ductile concentrically braced frame. And in here, the U factor is 2 and SP factor is 0.77, and that is in line with other steel structures not defined above. So in here, more or less, we are going a little bit of, conservative, but that is okay, because ultimately wind load shall be the one that shall be governing your design. So we can consider mu factor as 2 and SP as 0.77. So mu factor can be taken as 2 and SP as 0.77, considering the limited ductile concentrically braced frame. Hazard factor. So in here we can assume that, let us say we are proceeding with the Adelaide location. So we can proceed with the hazard factor Z as 0.1 here. And probability factor in our case, as this is not a, we can say, a school building or a hospital building, so we can proceed to probability factor KP as 1. And site subsoil glass, we can assume it as B itself. And the last factor is basically the KT factor. So that is also a standard, calculation that is given in the code itself. As of now, we can click on OK and then again click on OK to find out the actual height. So in here, the Z here, you do need to check this particular area. So Z here is 0 and Z at the top is approximately, we can say, 8 meters. So the height of the pipe is approximately 8 meters. So this is the equation here. So here you can see that KT factor is 0.11 for moment resisting steel frame. And for centrically braced steel frame, it is a little lesser, that is 0.06, but that is not our case. So we can proceed with either entering the time period, that is, we can calculate time period with this particular formula. HN, we already know that it is approximately, we can say, 8 to the power 0.75. KT we also know. So So we can enter 8 to the power 0.75 into 1.25 into 0.11. So 1.11 is kT, and we can see here that the time period that is coming is approximately 0.654. So we can go to the define load patterns here, and we can just enter the ES1170, left click on modify later and load. In here we can enter the user defined time period also, that is 0.654. So we can remember all these values because we shall be entering the same in the y also. So b 1.1.772 and 0.654, b 1.1.772, and time period as 0.654. The only difference is the direction in which it is acting along the y direction. So now we have already defined the earthquake loading also. We can click on analyze and check model, select all and then OK. So there are these two errors, that is at level 3, C16 and C18. We can just simply copy paste these errors there. It should not have come, but if they come, we should know how to resolve. So we can simply copy paste this in the notepad file, and in here we do need to go to this particular coordinate. So we can go to the level 3 here. So in this, we do have a coordinate of 21 meters, y as 6. So x21 and y as 6. So we can enter, go to x21 here. And y as 6. So I think this beam is like replicate. We can just simply press delete now. I think there is some issue here. We can press Ctrl and W option to switch off the releases because that is taking a lot of space to think. So we can press 3D view again, and I think there is some problem with the bracing arrangement here. Yeah, so I think instead of having a, so what we do need to here is that in our case, we do know that there are these C16 and C18 and C24 and C26. So we can go to the Control and W option, and in here we can select object assignment and labels. So when we switch on the labels, we can see the like names here. So these are C16 and C18. So this is the one that is causing the problem. So we can just simply delete the C18, that is a single member that has been modeled 2 times. Here also you can see C24 and C26. So we can simply select the C26. We can press undo here. So we do need to ensure that there are these two different beams here, not the one beam that is acting here. So we can press Control and then again click here. So this is C24 and this is C26. What we can do here is that we can just simply delete this and model the single beam again. So we can go to the draw beam column and brace. In here we can select here it again as pinned, and we can draw the beam from this point to this point. So now it is okay. So we can again go to the 3D view here again, and we can go to the display and undeformed shape, and we can just switch off the labels for the frames. Apply and close. Again, we can go to the analyze and check model. Left click on OK. So now we can see that model has been checked and no warning messages are generated. So we can just simply run the analysis and see that whether there are any kind of errors or what exactly are the like utilization and how the structure is behaving, and so that before applying the wind loads we do have some idea as to what exactly is the range of the section sizes that is coming, because ultimately wind load is the one that is like dependent on the sizes of the structural steel members and obviously the piping that is coming on the top. So we can see that there is this maximum deflection of 11.647 mm. So if we go to the rotate the 3D view here, so here we can see that at the center, like some of the members are deflecting, and here I think this is the area where we can see the displacement. So we can go to the display and deform shape, and in here we can select the case here as, let us say, piping is the SIDL, like I think that was name changed. So here we can see that there is this lateral deflection that is happening of 76.4 mm. So that is quite a high lateral deflection. Here we can see that under the case of SIDL. So we can go to the display and deform shape again. We can go to the load cases here, because ultimately I think when we have changed the name here in that particular location, that is the load patterns, we have changed it to piping. So we can just unlock the model here. Again, go to the load cases here. Under the case of SIDL, we do need to check that whether the load pattern is correct or not. So here we can see that load pattern is correct. So we can select PI, PI, NG, left click on OK, and then again left click on OK. So now it is like correctly modeled. And after that, we can again go to the plan view here. We can click on level 1. In here, we do need to apply some kind of live loading also. Either those live loading can be the part of the lateral loading itself, that is the piping loading itself, or we can, apply some kind of loading on the top arrangement also. So what we can do is that we can assume that the piping or the live loading on each of the member approximately, let us say it is in the range of uh, the area load. Let us say it is in the range of 200 or 300 kg per meter square. So that can be divided or distributed on all of these members. So if we assume that the live loading is 3 kN per meter square, if we multiply this with 1.5, so the number comes out to be 4.5 kN per running meter. So we can select all of these members here by selecting the all stories option. And we can select these members here. And we can go to the assign frame loads and distributed, and in here we can apply the live loading also. So 3 kN per meter square multiply with 1.5 meter center to center spacing gives us 4.5 kN per meter of the vertical load. So now this loading is also applied. So we can go to the display and undeformed shape. We can check the load combinations also. So in here we have already selected the dead load, live load, and all that. So under the case of 1.35 DL, we already have the piping loading also. So that is also like quite considered here. So we can go to the analyze and advanced Sapphire option. To save the time, we can proceed with the advanced solver. But if there are any errors in the model, we can proceed with the standard solver. We can go to the display and deform shape. We can go to the combo here, and in here we can select the deflection under the case of 1.35 DL. So here we can see that there is a lot of lateral deflection that is coming, and it is in the range of 106 and 122 mm. So that is like a lot of deflection here. So maximum lateral deflection that is coming is approximately 103 mm here at this point, and 104 here, 103 again here, and 102 here. Obviously that is under the, we can say, factored loading. So under the case of unfactored loading, this value obviously shall be little bit lesser only, but the behavior is same. So here also you can see that it's approximately 75 mm. So we can click on displacement along X, whether there shall be any contours here. No, there shall not be any contours. We can click on wire shadow also. So this was the original location and this is the final location. And if required, we can see the animation also. So here, so this is the arrangement, with which when we are applying the lateral loading, this is bending along the major axis and minor axis. So the thing is that if we see the undeformed shape here, we have applied the bracing in this particular direction, but there's no as such bracing in the horizontal direction. So that is why it is displacing a lot along the other perpendicular direction. So how we can do that is that we can go to the, we can unlock the model here, and we can go to the draw beam column and brace here. In here, we do need to select some heavy section. Let us say we proceed with 360 UV 44.7. Moment we can take it as pin because this is a shear connection frame only. We can go to the elevation along grid 1, apply and OK. The snapping is not correct. Here you can see there is some gap here. So this you do need to understand while modeling. So we can again go to the draw and snap options here. Again, we do need to select lines and midpoints and perpendicular projections. So we can again snap the beam from this point to this point. And then after that, we can, proceed on designing the other direction members also. So either we can have this kind of bracing, that is chevron or V bracing. So we can go to the draw beam column and brace, and we can go on quick draw braces option. So in here we can select 250 UV 52.7. Instead of, if we are selecting X here, this bracing shall be drawn something like this. But if we are making a V here, this bracing shall be drawn something like this. And what would be something like this. What would be here? It is not catching up. Yeah, this is the V bracing. But by default, it is not catching this secondary member here. Why I have provided secondary member here is because if we are making such a huge height of bracing, it shall not be simply passing in the design, because the longer the member, the lesser shall be the allowable compression moment. So we can proceed to the simple case, that is draw beam column and brace. In here we can select PFC parallel flange channel of 200. Moment release can be pinned. We can draw a beam from this point to midpoint, and then again close this member. Then again start arrangement from this point to this point and from this point to this point. So we can select all of these members here, go to the 3D view here, press Ctrl and R option on a keyboard. Y we can select it as 6 meters. Instead of -6, we do need to select +6 here. Click on just press Ctrl C and Ctrl V. Under the pressing Ctrl C and Ctrl V, select here Y as 6 and then left click on OK. So now the bracing has been modeled along the X direction now. So let us see that whether now, even now, that lateral deflection is coming or not. So now you should understand that, when the lateral forces are being applied on the steel structure, the bracing members are very, very important for the lateral stability. Otherwise, that structure shall simply deform and it shall not be, passing in the design when we are checking it for the serviceability limits as per the AS 4100 and 2020. So we can go to the display and deform shape again. Earlier, we were getting a deflection approximately 75 mm under the case of the serviceability loading. So we can left click here again. So now we can see that the maximum deflection that is happening is nothing. It is approximately 1.769 only. Earlier it was 75 mm. Here also it was approximately 75 mm. So that is how the bracing works. As soon as you apply the brace, the whole structure gets locked and you shall not be able to, proceed or deform anything beyond that. If we key like check this particular member, so this member is like deflecting 89 mm. So obviously this member is like quite under design. So we shall be increasing the sizing of these members. You don't need to worry about that. But just to uh, tell you the behavior, I hope the principal picture is now clear to you. We can go to the deform shape also here again and click on the mode shape here parameter. So if we see the fundamental mode shape here, the time period is approximately 0.457 against the 0.654 that we have calculated. So if we would have entered KT only and we would not enter the time period, so the ETAFs would have designed the this particular pipe rack for this particular time period only, that is 0.457. But as we have manually entered the 0.654, so that is why it is a little bit different. And obviously, all of these parameters do depend on the bracing also. The more you add the bracing, the lesser shall be the time period. So if we see the fundamental mode shape, so it is going in on the Y direction. And if we check the other fundamental mode shape, that is along the second mode. So, so for the second mode shape, we can see that it is torsion. And if we see the third mode shape, it is the local, we can say, deformation along the Y only. So that is like the, we can say, if you're talking about a dynamic behavior. But if you're talking about the simple areas in Australia, we don't need the dynamic behavior for this kind of structure. We can proceed with the static analysis also as per the ASW 170 part 4. So that is done, and deformation is also like quite controlled. So we can go to the, we do have to apply the wind load, but just to have an idea whether we are proceeding in the right direction or whether we want to increase the sizing also the members, we can do the preliminary first stage design also. So in here we can select the design combinations which are already selected correctly. Serviceability load combinations are also selected correctly. And in here we can select the AS4100 2020 and just click on the steel frame design option. So in here we can see that many of the members are failing in the design, but many of the members are also passing also in the design. So like this particular beam, this is failing in the design. So what we can do is that we can proceed with higher sizes also of this member. Let us say we proceed with 610. So under the 610, it is in many of the cases passing in the design. But in one of the case, it is, I think there is a little bit of problem there, so that we can, attend to. That is not a very major issue. But overall, more or less, our structure is okay. So all the section sizes that we have assumed are also okay. In here, we are having a lot of, we can say, uh, problem here. So let us see if we're talking about this particular number 310. We can simply proceed with the next available size, that is 360 by 44.7, and it's only passing in the design. So like this is also okay. So the thing is that we can do the optimization also, like here in this particular arrangement. If we are proceeding with this particular member, we can decrease the size of this member also. But again, here it is 310, it is failing in the design, so that we can increase. So what we can do here is that we can simply unlock this model. We can proceed for the, we can say, design under the later stages. So now we have to apply the wind loading also here for this particular arrangement. So this open structure wind loading arrangement is a little bit complicated because the softwares are not that in aligned with AS4100. But if we would had selected, let us say, if we are proceeding with the load patterns here again, just make a separate load case here as wind load US, and type we can select it as wind. Auto later load we can select it as, let us say, uh, this ASE 7 2022. Left click on add new load. We can click on modify later load here. In here we do have a option of open structure here. So include frame objects and open structure. So in this, let us say we click on OK, and then again left click on OK. We can go to the display, load assigns, and frame. We can click on wind load US and apply. So in here we can see that how the wind load is automatically applied on all the open frame structures as per the open structure wind loads. But this feature is not there when we're talking about the Australian standard AS1170. So that is a little bit of difference when we're talking about the, obviously, the software that is made in US for the US. But for Australia, it is Spacegas. Spacegas has their own, we can say, advantages also and disadvantages also. But I'm just showing you an idea as to how exactly the loading is applied. We can just click switch off the show loading values and switch off the joint loading also. So this is how we can apply the wind loading on all the, we can say, frame structures. So ultimately this loading also becomes a very heavy loading. So but this was just to show you that how the open structure wind loading is applied. We can click on delete loads here, and then again left click on OK, and then after that we can again go to the load patterns here, and now ultimately we are not proceeding with the open structure wind load because that is not supported as per the AS1170 2021. If we click on the modify load here and then click on modify later loads here, there is no as such option for the open stories or the open steel structure. So what we need to do here is that we do need to manually, have an idea of the approximate loading that is being applied on, or has to be applied on all the structures as per the ES1170 part 2. So we can click on none here, modify load, left click on OK, and then again save this model.